so in this part of the video, we will continue to use the power series method to solve differential equations with non-constant coefficient. So let's say you are given the differential equation in this form. So P of x is the coefficient, the non-constant coefficient to the second derivative of y. So P of x times y double prime plus Q of x times y prime plus R of x times y equals to 0. And we will be dealing with only polynomial coefficients, i.e. the functions of P of x, Q of x, and R of x are all polynomial functions. Okay, so before we proceed to use the power series method to solve differential equation, we need to determine if the x equals to x naught is an ordinary point or not, because it only works, this power series method only works if x equals to x naught is an ordinary point. So we have two types of point, which are the ordinary points and a singular point. So we say that x equals to x naught is an ordinary point if provided both of these ratios. So we given the ODE like in the standard form, like what you saw in this slide. So you find out qx over px and rx over px, and if both both quotients of these functions are analytic at x equals to x naught, then we say that x naught is an ordinary point because these two quantities will have a Taylor series around x equals to x naught. And for most problems, P of x naught is not equal to 0. So anything that is not an ordinary point is called a singular point. So if it's a singular point, i.e. that given this qx over px and rx over px, they are not analytic, we need both to be analytic, okay? So if any one of them or both of them are not analytic at x equals to x naught, then it is not an ordinary point, then it is a singular point, so we cannot use the standard power series method to solve the differential equation, so we need to use other method. Right, so the basic idea to finding the series solution to a differential equation is to assume that we can write the solution as a power series in this standard form. So you've seen this standard form several times now. And then we try to determine what the ANs, the coefficients need to be. So we can only do this to if x equals to x naught is an ordinary point, and we will say that this equation 6 here is a series solution around x equals to x naught. So let's do this example straight away. So you need to find a series solution around x naught equals to 0 for the following differential equation. So you are given y double prime minus xy equals to 0. So we want to find the solution, i.e. the yx, and then the the corresponding coefficient of ANs, A0, A1, A2, A3, and so on. So first what we do is we compare the given differential equation to the standard form. So the standard form of a differential equation is this: P of x times y double prime plus Q of x times y prime and R of x times y equals to 0. So from here, you see that the P of x equals to 1, Q of x equals to 0, and R of x equals to negative x. So you can find out if px over qx over px, so qx over px is 0, and rx over px is negative 1. So both here, not negative 1, i.e. negative x. So both the ratios here are analytic at x equals to x naught. Or in this case, you can see that straight away. So since P of x equals to 1, okay, P of x equals to 1. So for this differential equation, any point is an ordinary point. So including x equals to x naught equals to 0 in this case. So because given any point, it would be analytic. It would be analytic, i.e. it would be defined. It can have a Taylor series solution around x equals to anything. Okay, so let's say we assume the given solution. Okay, so now we'll start the actual work. So given y double prime minus xy equals to 0, and we want to assume this solution is, this y is the solution to the given ODE. Okay, so this y is n starting from n equals to 0 to infinity a of n x minus x naught to the power of n. So here our x naught is 0, so we can just simplify this equation. This one is 0, so we just have an times x to the power of n. So from here, you can have the y prime of x is thus equal to summation of n equals to, from n equals to 1, then an x n minus 1, and also y double prime of x is thus summation from n equals to 2 to infinity n times n minus 1 a of n times n x n minus 2 x to the power of n minus 2. Right, so next step is we put this into the ODE. So we put this y double prime into here and this y into here, and we don't use any of this y prime because there isn't one. So we put that. So we have from n equals to 2 to infinity, this one, this term, minus x times y. So our y is this, equals to 0. Okay, so what's next is we want to put all the coefficients outside the summation notation inside. So we put this x inside here. So we will end up with this expression instead. And x, now that we put the x inside, we have n plus 1 equals to 0. So what do we do next is that we want everything to have n the same index and the series starting from the same value of n. So now we want to first shift the series so that we can get x to the power of n only. So you can do the long cut or shortcut, but I obviously prefers the shortcut. So the first term, let me change this point here. Okay, so here, the first term here, I'm gonna, this one I'm gonna add 1. So everything I add 1, add 1, add 1. So this one I minus 1 down here. No, not, sorry. This is not minus 1, right? So this is minus 2. Okay. Right. Okay. So this is plus 2 then. Plus 2, plus 2, plus 2, plus 2. Then this is minus 2 since I added 2 up there. So I minus 2. So now we start from n equals to 0 to infinity. And then n plus 2. And minus 1 plus 2 becomes plus 1. And then a n plus 2. Then x to the power of n. Okay. Then I'll do the same, I'll shift the index in the second term here. Okay, so here I want to minus 1. So everything I have to minus 1, but here I have to add 1. So here n equals to 1 until infinity, a n minus 1 x n equals to 0. So now that we have x to the n, but now our series do not start at the same value of n. So now what we do is that because we can't be, minus 1 here and then we have to add 1 up here. So what we do is we take out the term at n equals to 0 so that both series will start at the same value of n. So for this first part of the series, I will just take out when n equals to 0, I will have 0 plus 2, 0 plus 1, a0 plus 2 and x0. That will give me, when n equals to 0, it is 2a2. Okay, so when I take out the term 2a2 out, and then I can start the series from n equals to 1 because I already take out the n equals to 0. So this is your S0 and this is your remainder R1, if you recall the earlier part of the video previously. Okay, so now I can start the series at n equals to 1 and copy the whole thing. And also the second series here, this one also starts from n equals to 1. Yeah. So now it starts at the same index of x and the same value of n, starting point, and then we can combine. Okay, we can combine the series. So we still have the 2a2, and we have this n equals to 1 to infinity, and then we can factor out the xn and put the coefficients together. So n plus 2, n plus 1, a n plus 2 minus a n minus 1, the whole thing factor out, and then multiply with xn, everything equals to 0. So now this is the, okay, I have actually put down the step-by-step here. So actually we are now we have done this, we got this, we got this, we got this. So now in step 5 is to set all the coefficients to be equal to 0. Because when you compare the coefficients, then everything is equal to 0 on the right hand side. So then we can put that. So when n equals to 0, you have this 2a2 term. So 2a2 will be equal to 0. Okay, and then when n equals to 1 and 2 and 3 and so on, you have your coefficient n plus 2 times n plus 1, a n plus 2 minus n minus 1 equals to 0. So we have these two equation for step number 5. And then we go to step number 6, which is to solve the first as well as the recurrence relation. And then we'll do this step 6, 7, and 8 all together. Okay, so next we want to see the pattern there. Okay, so step number 6 is to actually solve for the coefficients. So for this, 2a2 equals to 0, then you can solve it directly that a2 equals to 0. But right, so now we want to see what happens when n equals to 1, when n equals to 2, n equals to 3, and so on and so on. So let's see what happens when n equals to 1. So when n equals to 1, the coefficient becomes 1 plus 2 times 1 plus 1 times a, 1 plus 2 minus a minus 1 equals to 0. So here you have 3 times 2, a3 minus a naught equals to 0. So you have a3 equals to a naught over 3 times 2. Okay, so let's leave it at that first because we want to see the pattern. Okay, now we do n equals to 2. So when n equals to 2, you plug into this equation for the coefficient. So you get, 4 times 3, a4 equals to a1. Or initially you get minus a1 equals to 0. So then you get a4 equals to a1 over 4 times 3. Okay, then you repeat with n equals to 3. So all of these are in your book, okay, in your notes. I'm just explaining all the way through. So for n equals to 3, you have 3 plus 2 times 3 plus 1, a5 minus a2 equals to 0. So your a5 equals to a2 over 5 times 4. And your a2 is equal to 0, can, right? So a2 equals to 0, so your a5 is 0. Then for n equals to 4, we still haven't seen the complete pattern yet, yeah? So that's why we need to go on and on until we see the pattern. Okay, so for n equals to 4, you have the coefficient 4 plus 2 times 4 plus 1 times a6 minus a3 equals to 0. So you have a6 equals to a3 over 6 times 5, and do you have any A3 there? So yes, yeah, you have this A3 equals to A0 times 3 over 3 times 2, so your A6 is thus A0 over 6 times 5 times 3 times 2, okay? Now we are beginning to see the pattern. So now when n equals to 5, you have 5 plus 2 times 5 plus 1, and then A what? A7 minus A4 equals to 0. So you have A7 equals to A4 over 7 times 6. So do you have any relations on A4? Yes, you do. So you know that this A4 is equal to this A1 over 4 times 3. So you write that down. So A7 equals to A1 times, divided by this one you just bring, and then 4 times 3. Now we want to continue to see if we get another pattern. Okay, n equals to 6. So you have 6 plus 2 times 6 plus 1. A8 minus A5 equals to 0. So A8 is A5 over 8 times 7. And you know A5 is previously equals to 0 because A2 is 0. So here A8 is also equals to 0. Right, so now we kind of starting to see the pattern. Right, so what are the pattern that we see? So try it. This is the tricky part of the power series actually, to see the pattern. So A3 equals to A0 over 3 times 2, and then A6 equals to A0 over 2 times 3 times 5 times 6. And then, so we suspect that from here, we suspect that the pattern would be such that, so here A3 and A6, so we suspect that A9 will be equals to A0 over 2 times 3 times 5 times 6 times 8 times 9. And thus, we would suspect that from these three patterns, we will get that when for k equals to 1 and 2 and 3 and so on, we will get that a sub 3 times k, because when k equals to 1, a times a is sub 3, okay, equal to a naught, that doesn't change, and 2 times 3 times 5 times 6 times whatever until 3k minus 1 times 3k, because you see the pattern here. Okay, you see the pattern. Okay, so that's one pattern. And then what's the other pattern that you can spot? Okay, so now from A4 and A7. So from A4, so A4 you have A1, A4 equals to A1 over 4 times 3, and A7 you have equal to A1 over 7, 6, 4, 3, but you can write down from 3. And you suspect that maybe A10 will be equal to A1 over 3, 4, 6, 7, and 9, and 10. So then, from here, you can spot the pattern, and you can deduce that for k equals to 1 and 2 and 3 also, you may get that a sub of 3k plus 1, because here, from compared with the blue ones here, it's just 3k, but now instead of A3 you have A4, instead of A6 you have A7, instead of A9 you have A10, then the 3k must plus 1. Okay, so this is A3k sub 3k plus 1 equals to A1 over 3, starting from 3, then 4, and then 6, and then 7, and then so on and so on until it's 3k and 3k plus 1. Yeah, so that is the second pattern that we can spot. And then you can also spot another pattern for this A2, because A2 equals to 0, and A5 equals to A2 over 5 times 4 equals to 0 also, because A2 is 0. And then your A8 is also A5 over 8 times 7, which is A2 over blah, blah, blah. Doesn't matter because eventually A8 is equal to 0 too. So for K equals to 0, equals to 1, equals to 2, the pattern is such that A sub 3K plus 2 equals to 0. Okay, because you see that the pattern is A2, A5, A8. So you also suspect that A of what now? A11 maybe, yeah? A11 is also equal to 0. Because this is what you suspected from the pattern that you see from A9, A10, A11. So you suspect that when K equals to 0, 1, and 2, and this will happen and it equals to 0. So what you do now is all right, now you kind of solve the value of A's, A sub n, okay? So next is you want to collect all these terms into one single power series solution. So go back to the top of the whiteboard. Okay, so here. So now, previously you you suggested that this is your solution to the power series, to the differential equation in terms of power series, an x n. So when you expand this y, you will get a naught plus a1x plus a2x plus a3x cubed. And so on and so on until a sub 3k x 3k plus a sub 3k plus 1 x 3k plus 1 and a sub 3k plus 2 x 3k plus 2 and so on until infinity. So you see the pattern. Now you can start plugging in whatever values that you know. Okay, so y of x equals to a naught, we don't know, and plus a1x plus a2. So a2 is 0. Okay, so a2 is 0, a5 is 0, a8 is 0. So but now let's stick to the terms that we see here. So and then a3. So a3 is what? A3 is a naught over 3 times 2, right? So now you put the terms as a naught over 3 times 2 x to the x cube. And then a4, what is a4 now? a4 is a1 over 4 times 3. And a5 is 0, so you don't have to include that. So here, instead of a4, you put a1 times 4 times, over 4 times 3. And so on and so on. So when you reach a sub 3k, so a sub 3k is, previously a sub 3k is a naught, in terms of a naught is 2, 3, 5, 6, so on and so on until 3k minus 1 and 3k x to the 3k plus, so for this a sub 3k plus 1, a sub 3k plus 1 equals to, in terms of a1. Okay, so you have 3, 4, 6, 7, so on and so on until 3k times 3k plus 1 times x to the power of 3k plus 1 plus, and then 0, right? The a sub 3k plus 2 is 0, so just just stop here for now, and then plus on and so on until infinity. So here is the okay, so you see the pattern that. Then what's the next step? So now you see the pattern and you get the solution. So step 9, final step, is to collect up all the terms that contain the same coefficient, factor the coefficients out, and write the result as a new series. Okay, so what you do is, all right, so now you have everything in terms of A1 and A0 and A1. So you collect all the terms in terms of A1 and A0. So y of x is equal to A0 1 plus, what do you have? One over 6 x cubed, or just x cubed over 6, plus whatever, and then x to the k. I mean, by right, I should put all this dot 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 first, and then x 3k over 2, 3, 5, 6, 3k minus 1, 3k, and then until infinity, plus with now A1 terms. So A1 starts with x, and then plus x4, 4 times 3 is 12, and then plus so on and so on until x to the power of 3k plus 1 over 3, 4, 6, 7, 3k times 3k plus 1, and so on until infinity. So that would give you the actual solution of y of x. So in this simplified form, okay? So you see that if you are given the original differential equation in this form, y double prime minus xy, so you have a non-constant coefficient here, which is x or negative x. So you can use a power series method to follow through these solution steps. And the challenge is usually when you need to see the pattern here, and then you need to just collect all the terms that contain the same coefficient, factor it out, and write the result as a new series. Then then you stop there. Okay, so this is actually your solution, your proposed solution to the series given. I mean to the DE given. But now you cannot find out what are the values of A1 and A0 because you're not given any initial or boundary condition. But if you're given initial or boundary condition, so you may find out what are the values of A0 and A1. Okay. Right, so take a break here before we continue to the next example.